So she will speak about the galactic cosmic ray signatures and coronal of CM.
So hi everybody, I am Mateja Dumbovic. I come from Hvar Observatory, Croatia. For some of you who were at COSPAR last week, this will be a very familiar talk, but perhaps with better slides this time. Okay. So as Alexander said, I will talk about signatures that coronal mass ejections make in the galactic cosmic ray flux. And this is because in general, solar activity modulates galactic cosmic rays and on different timescales. On timescales of 1 to a couple of days, we have two notable types of interplanetary transients with sources from the sun. And these are coronal mass ejections. This is shown on the left. And co-rotating interaction regions. And of course, the solar sources of these two interplanetary transients are different, and so are their properties. So CMEs are sporadic events. They occur typically 1 to several during the minima, and during the solar maximum, you can have even tens of them a day. Co-rotating interaction regions are actually reoccurring events. And this is because their sources are actually coronal holes, and they rotate with the sun, and so they occur every 27 days or so. Whereas CMEs actually come from eruptive processes on the sun, which are totally stochastic. And actually what we think that the CMEs are, in this image, this yellow thing here, that they are actually kind of closed magnetic structures with a helicoidal magnetic field, which is winding around some central axis. And as they move through the interplanetary space, they kind of drape the interplanetary magnetic field, compress it, and cause a so-called sheet. And then when you go with your spacecraft through the CME, what you observe is the sheet and then this magnetic structure. And then sometimes they are fast enough so that in front of this sheet, you can also see a discontinuity or the interplanetary shock. On the other hand, co-rotating interaction regions, which I said, they have a source in a coronal hole. Coronal holes are areas in the sun from where the high-speed streams are coming. And these high-speed streams in the interplanetary space, they kind of push against the solar wind. So if you go through your spacecraft through a co-rotating interaction region, first you will see the solar wind, then a compression region. Somewhere inside the compression region, you will see the stream interface. This is a point where the two streams kind of bump into each other. And after that, the high-speed stream. So you can see that both of these, they have kind of sub-regions, and they have quite different properties. And actually, I will focus my talk today on this magnetic structure, the flux rope, ejecta, or CME. Okay, so of course, because they have different properties, they also cause different depressions in the galactic cosmic ray count. So this is given now in the first panels of both left and right image. What you can see that for CMEs, we have kind of an asymmetric depression, and you can kind of see that there are two regions. So the first one, there is like a quick drop, and then you have this more symmetric kind of depression. And these two correspond, of course, to the shock sheet region and the ejecta region or the CME region. And for the co-rotating interaction regions, just to kind of mention, so they have a more prolonged depression, which is more symmetric, and it lasts until the end of the high-speed stream. And here you can see that for CMEs, actually after the magnetic ejecta passes, you still don't reach the previous level of galactic cosmic rays, but you have like this very slow recovery. So if you want to model this, and we do want to model this, right? You have to start, of course, with the transport equation. Typically, the transport of GCRs in the heliosphere is described by the Parker equation. which kind of has four main mechanisms: the convection by solar wind, particle drifts and diffusion, because the heliospheric magnetic field is not homogeneous and it's not constant. And also you have the adiabatic energy loss, because the heliospheric magnetic field is expanding. And if you want to, and some people, I think in this session will give a talk about modeling galactic cosmic rays, and especially these short-term depressions with the Parker equation, you have to solve it numerically. What we wanted to do is kind of describe it analytically, and then you need to, of course, make a lot of assumptions. So for CMEs, the main assumption is actually that the diffusion is the main mechanism which produces this depression. And why? This will be maybe more visible on this picture. So when you make this kind of plot, this is now a fully idealized a sketch of how the CME looks like in the interplanetary space. So you have the shock sheet region here. Then in the red, you have the CME or the magnetic ejecta, and then you have some kind of recovery region. And this sketch here kind of shows how your spacecraft goes through this, what you observe in situ measurements. So when you look at the sheet region, what you will see is that the field lines outside of the sheet region and inside are connected. This means that the particles can go through the shock, right? And enter the sheet region. This automatically means that you can have basically all the mechanisms that you have in the Parker's transport equation. But if you have a look at the magnetic ejecta, what we kind of visualize is that it is closed to the sun and it's not magnetically connected to outside. This means that the only way particles can enter is by some perpendicular transport. And what we think is that actually the CME, when it starts at the sun, doesn't have any GCRs inside. It's totally empty of GCRs, which means as it travels through the interplanetary space, it has to kind of fill up with GCRs. And the only way they can enter is by perpendicular transport, which is very inefficient. That's why at certain point in the heliosphere, you basically observe depression. And we did this with our very simple analytical model, which we called form mode, a couple of years ago. And it's basically a time-dependent diffusion expansion equation. Why diffusion expansion equation? Very simple, because CMEs at the sun, they start very small, and then as they propagate in the interplanetary space, they expand self-similarly. Basically, they are just bigger scaled versions of themselves from previous times. Okay, so what we wanted to do is actually use this very simple analytical model to see whether we can get some, whether we can mimic some profiles of Forbush decreases, these depressions in the heliosphere. So what we simply did is we make a best fit function using nonlinear best fit and using this form mode analytical function. Just to note, the form mode function is basically a Bessel function which has some exponential addition which describes how it evolves in time. So at any certain point in time, your Forbush decrease profile will be a Bessel function, and this exponential part will just tell you how big the amplitude is. Okay, so we kind of identified CMEs in the near Earth space using SOHO Effin detector. We followed the typical properties criteria for CMEs, and that is it has to have a rotation of the magnetic field, low fluctuations, increased magnetic field, total magnetic field, expanding profile in the speed, this is speed, and low temperature. And you see here that there is a associated depression. And of course, when you make a best fit function to this profile, which is shown here, you can also calculate goodness of fit by using mean standard error. But the problem is you don't know what this mean standard error means, right? So for instance, in this example, we got this number, but we don't know how good or bad this is. And in order to see how good or bad this is, we actually kind of tested our best fit function using synthetic measurements. What are synthetic measurements? So basically we take this four-mode analytical function for a certain example. So this is like a very nice curve, symmetric curve. It's given here in black. In all these images, it is absolutely the same. Sorry, not the black one, the blue one. Sorry, my mistake, the blue one. And then what we do is we apply some noise on it. So we apply some Gaussian noise in the Y direction, in the X direction. We introduce some gets. Basically what we do is distort it, okay? This is how we get the synthetic data. And when you look at here, you can have some nice synthetic data. Like for instance, this is a nice example. It looks totally realistic. And you can have something which is totally like here, the red dots, you wouldn't say that this is a Forbush decrease, right? So with different levels of noise, we can actually test how our best fit function will look like. And the best fit function in all these examples, this is the black curve now, it always fits the data, although the data looks kind of crappy. But what you see is that there is a difference between the real theoretical curve, the blue one, and the black one. So basically what we wanted to test is how now the mean standard error behaves, actually how the difference between the best fit function and the real function behaves compared to the mean standard error. And this is given in this hugely noisy scatter plot over here. And at first sight, it doesn't look like you can get much out of it. But what we noticed is that when you have data which visually looks like something you would fit, it would always either follow the identity line or lie somewhere below 0.01 mean standard error. On the other hand, if you have this kind of data here, like this red one, when you look at that, you would never say that this is a Forbush decrease. So as an observer, you would never try to fit this. And this is actually the data which you always find either really far away from the identity line, or if it's on the identity line, it's always after a mean standard error of 0.01. So our conclusion from this is that if you get a fit which is below 0.01 mean standard error, it should be somewhere in this small square here around the identity line, meaning that your Forbush decrease amplitude error should be below 10%. Okay, and then we tested this on a bunch of events, not bunch of events, 30 events from Soho Effin that we found. We searched a specific time period from stereo era. I don't want to bother you right now why we chose this specific time period. There is a reason, but that's a whole new study which is following this study. Anyway, we found 30 events and we applied this best fit function on all of them. These are a couple of examples. What we found is that actually we managed to fit each and every one event, which is good. The mean standard error is always acceptable, meaning that the amplitude should be within 10% of error. And on this plot, I show you kind of a comparison of what the observer would calculate the amplitude is and what we get with the best fit function. And you can see nicely that, that it follows identity line, meaning that our code works almost as good as the observer, which is always great when you try to make some automatic code. Okay, so these are some takeaway messages. So we can use galactic cosmic rays as signatures of interplanetary transients. And we can model CME associated Forbush decreases. Of course, we need to take care that we model each region separately. We can model the ejecta part or the flux flow part or CME part, whatever you want to call it, by this analytical diffusion expansion model, which we call 4 mode. And the best fit function that we made, it can fit relatively easy and simple. This ejecta related Forbush decrease profiles, and it works quite well, almost as good as the observer. So that's it. Thanks.